Welcome. Today's lesson is entitled Compositions of Functions Day 1. At this point in our curriculum, we've been able to combine two functions together in 4 different ways. We've added functions, we've subtracted functions, we've multiplied functions, and we've divided functions. Well, there's a 5th way that we're going to go ahead and combine two functions together to create a 3rd, and obviously that's entitled Compositions of Functions. So the best way for me to lay this out is through an investigation, try to kind of see what I'm looking for and what this scenario represents, and then obviously we'll take a look at the notation, some algebra behind that, and then maybe an application at the end as well. All right, well, let's start it out here with the investigation on the top of your paper. It says very simply, a patient is given a drug with the side effect of raising the heart rate. And so what I have here in this table is a relationship between two variable quantities. And as the patient is given the drug, we've got the drug level, and there is the heart rate right there. And I would argue, obviously, that one of these quantities depends on the other, and we maybe should write that off to the side. Not that it's vital, but I think it wouldn't be a bad idea. So which depends on which? Well, I'm hoping you would agree with me that really the heart rate depends on the drug level. So the heart rate is the dependent variable quantity, and the drug level would be the independent variable quantity. And you can see from the values in this table exactly what this specified up here. As the drug level goes up, the heart rate is increasing. And that's all we're going to put in this conclusion right here. It doesn't have to be dramatic by any means. Very simply, the more drug in the system, the faster the heart rate. However you want to do this, you're more than welcome to kind of paraphrase me if you'd like, but the more drug in the system, the faster the heart rate. Heart rate is increasing as that drug level increases as well. All right, perfect. So we've got a function. Heart rate is dependent on the drug level. Heart rate is a function of the drug level. Excellent. Well, there are 2 other quantities that probably relate very nicely in this particular situation, and that would be the drug level and the time. And so you can see now I have a secondary function dealing with these 2 variable quantities right here. I would make probably the same argument. One quantity depends on the other, and I'd ask you which is which in this particular case, and if you want to write that off to the side, that would be excellent. Here we have the time in hours, and here we have the drug level in milligrams. And I'm hoping you wrote off to the side here that the drug level depends on time. And so drug level is the dependent variable quantity, and time, of course, is the independent variable quantity. Looks great. What do you notice, of course, with the drug level over time? Seems like it's decreasing. The body is able to metabolize the drug, and the levels go down. All right, so again, doesn't have to be dramatic. Let's put something like that in place. Again, feel free to write what you want here, but I've got over time, the body metabolizes the drug, and hence the level goes down. Okay, that looks absolutely great. 2 functions based on the situation at hand here. What I want to do is somehow put these together in a way that makes sense. So I have 3 blanks right here. I'm going to fill in the first 2 based on what we've already concluded, and then the question is, what can I maybe derive as a 3rd idea, as a 3rd connection between our quantities? So here's what I wrote. If you could do the same, that would be great. So the first table and the first function is the heart rate is dependent on the drug level. So the heart rate, which is our outputs, is dependent, or here's how I'm going to write it, is a function of, that's great right there. So we have heart rate is a function of the drug level, output in terms of the input. Okay, that looks pretty good. So that's the first scenario. The second scenario would be this, where we said the drug level is a function of time. So let's put that in. And I'm going to be doing inputs and outputs here because we'll talk a lot about that over the course of the lesson. So in this case, the drug level is the outputs. And so the drug level, as I said, is a function of time. time being the input. All right, so let's see what we have in the first two lines, and the question is, what can we put on the third line? So the heart rate is a function of the drug level. I'm just going to put a little and right there. So and the drug level is a function of time. And so I'm going to put a little so right here. What can we conclude? Maybe you can tell by my inflection as I read it one more time what I'm looking for right here. If you can, great, write it in already. If not, just wait a sec on it. But here's the situation. Heart rate is a function of the drug level, and the drug level is a function of time, so it seems like the heart rate is connected to time as well, and heart rate is a function of time. So we're going to combine the first two together to create a third function right there. How does that look? And notice the situation at hand here. The drug level, which was the input of one function, is the output of another function. That's what connected these two quantities together. Heart rate, then, is a function of time. And, of course, if you look at your notes worksheet right there, and I'll go to my next board, notice what I have for you, a table now relating those two as a function. Heart rate is the dependent variable, time is the independent variable, and you can see all those values represented nicely in this table right here. Excellent. Okay, well, let's go get them. This situation is an example of a composition of two functions. Okay, and the idea, as we saw in our investigation, that the output of one function becomes the input of a second function. So write that in for me. Again, we'll look at the notation, we'll look at the algebra behind it, etc., there. So let me just make sure I have my phrasing correct up here. There we go. So the output of one function becomes the input of a second function. For our investigation, that quantity happened to be the drug level. Notice it's the output of one function and the input of another function. We combine those together and we get this, heart rate as a function of time. All right, really awesome. Well, let's get into our first piece, which would be the notation. And you can see this a couple different ways. 99% of the time, I'll gravitate towards one of these two notations, but you should be at least familiar with the other one. So what this basically means, each side of the equation represents the same things. It's just two different ways to write it. This is f composed of g of x. Again, f composed of g of x. Now, for our purposes here, I'm going to probably use this one, again, really an overwhelming majority of the time. I just like this better. I feel like it has more meaning written like this. It's just my opinion on that. But definitely if you kind of look in a textbook, or maybe I put it in some of your notebook as well, just be comfortable with that piece. The open circle is not multiplication. It is a composition. And so it's good to just get a sense of what this reads as and then what it'll look like. So this would read, as I already mentioned, f composed of g of x. There's that idea of composition. So f composed of g of x. That's good. And there are all sorts of combinations we can create. So if you look right over here, of course, I just have the reverse, and this would be just g composed of f of x. Again, I'll be using this side much more frequently, but g composed of f of x. So again, just that's how we would read it as. So let's get it on. G composed of f of x. Okay. Now it's good to kind of see this in action. We've looked at this flow chart maybe once or twice before over the course of our curriculum, but it's good to really see this and how it plays out. So here's what I have, and as a matter of fact, I could do this again any number of ways. I'm going to do this particular situation. It is probably the most common that we're going to see, so I'm going to go towards this. And here's the idea. If I want to look at what f composed of g of x means, I always, of course, start with my input. So our most generic input is x. So I start with my first input. Now based on the way this is written, as you can see, our input goes into the g function. So let's go ahead and get our little function machine going. Oh geez, I can never draw these well, but there we go. So there's our function g. X goes into the g function. Our g function tells us what to do to that input. And after it manipulates that input and performs the rules on it, out comes g of x. Does that kind of make sense? And we've seen this before, and this is actually where we stopped. Something goes in, something goes out. Input, output, of course. Now here's what's kind of interesting about this piece. This is not the end game as far as our compositions are concerned, because that output, as it says, the output of one function then becomes the input of a second function. So that output now goes in to another function. Well, here it is. Here's g of x, guys. You can see why I like this notation better. Here is g of x. What function does it go into and get manipulated on? It goes into the f function. So let's go ahead and make our little function machine one more time here. Oh boy, that's not too bad. There we go. And so you can see g of x now goes into the f function. Our f function tells us what to do to this. And after it does it, out comes f composed of that g of x, our output. And if you look back to the investigation at the top of the page, this is exactly the situation that unfolded. We started with time, and then we got the drug level. Instead of stopping right there, from the drug level, we were able to get the heart rate. And so as a result, what we determined is then the heart rate is simply a function of time. Pretty cool, huh? All right. So we have our notation in play. We have how it flows from one to the next and to the next. Now let's just go get the algebra behind it. So the easiest thing for me to do, at least from my perspective, is to just start out with some basic functions, go through some of the combinations that we may see, and notice we have two individual functions. What we're going to do is combine them together to create a third function. So always remember that. That's what we're doing. We're combining functions together. Not adding, not subtracting, not multiplying, not dividing, but a fifth operation dealing with what's called compositions of functions. All right, so f composed of g of x. Once you get it the first time around, it really shouldn't be too bad, to be honest. But let's see what we're looking for here. So I guess take a look at this piece right here. Do you see that we want f composed of g of x? Well, what is g of x actually equivalent to? Well, as you can see on the board, g of x is 2x plus 5. So for right now, just I want you to circle that 2x plus 5. You can erase it in a little bit if you'd like. And what we're going to do is, this is the output of one function. Then this becomes the input of the other function. So it replaces the x's in the f function. And that's how it's going to play out, everyone. So the output of one function becomes the input of a second function. And so that's what it means. And you can see the notation unfold right here. We want to take g of x and replace the x's of the f function. And now we have f composed of g of x. Okay, if that's not clicking, maybe it will by the time we hit B or C, etc. Down the line there. Otherwise, please feel free to ask at any point. Okay, so what would this function look like if the 2x plus 5 would be the inputs of the f function? So in this case, it looks like it would be, instead of x squared, it's 2x plus 5 squared. Instead of x, it's just 2x plus 5, and then minus 1. So we're replacing the inputs of the f function with g of x. That's probably the best way to describe that piece. Okay, well, you do have to simplify things, so kind of go through the motions if you would. You can get ahead of me a little bit on this if you want. We do need to do 2x plus 5 squared. Do you want to go ahead and FOIL that for me? Then we'll add the 2x plus 5 and then the minus 1. Well, I FOILed this out, and I ended up getting 4x squared. Looks like I'm getting a 20x and a 25. And then no need to keep the parentheses there. Not much more I'm doing with that, 2x plus 5. And then just minus 1. So just, again, let's put this in standard form if we can. And as a result, looks like I'm getting 4x squared. Combine the x's, I'm getting 22x's. Combine the units, and it looks like I'm getting 29. 25 and 5 make 30 minus the 1. And so that would be our answer right there. Let's box these up because it's maybe going to get a little convoluted in here. All right. And that's how it would play out. I'm going to do just a touch of erasing at the top because our second situation is going to be different than the first. That was f composed of g of x. So g of x replaces the inputs of the f function. Now, obviously, again, we can do this any number of ways. So what do you say we go ahead and do g composed of f of x? So if you take a look, we're going to have f of x, which is defined as that right there. That is f of x. And that is going to replace the inputs of the g function. So that's just going to go right in here. Again, same situation. So f of x replaces the inputs of the g function. This is what f of x is defined as, and so it goes in for the x's of the g function. Hopefully by now it's clicking pretty well. Again, feel free to always go ahead a little bit if you need, but I'm seeing something like that right there. Let's do the same simplification. This one's a little easier. How about a 2x squared and a 2x and a minus 2? Add the 5. And looks like I'm going to end up with 2x squared, 2x, and 3. There we go. Looks good. So 2 out of the 5 taken care of there. Looking really nice. Let's go ahead and do letter C. So this one is almost a little bit of a recursion. Again, any combination works here. So in this case, I'm looking for g composed of g of x. So remember what the situation is. Take g of x, and it simply replaces the inputs of the g function. So I do this on occasion. Here's g of x. I'll circle that, and that is going to replace the inputs of the g function. Well, there's only one input for the g function, and it's right there. So that 2x plus 5 goes in for the x value in the g function. It replaces its input. So I'm hoping, again, that that kind of worked for you, where instead of 2 times x plus 5, it's 2 times the g of x plus 5, and g of x is 2x plus 5. How cool. So 4x plus 10 plus the 5, 4x plus 15 does it. All right. So creating a third function using the original 2. That's the composition that we're looking at here. Let's get specific with some of the values. So we can do this again a couple different ways, but ultimately I'm starting with 1. 1 is going to go into the f function, and I'm going to get an answer. Whatever that answer is goes into the f function, and I get another answer. So here's what I'm going to do, and it's up to you how you want to play this out, but I'm going to start with 1, and it goes into f. So let's go ahead and put 1 in for f. And so f of 1 essentially. I'm going to probably do this off to the side a little bit, I'm just kind of thinking out loud with this. But f of 1 basically means 1 squared plus 1 minus 1. And are you okay with me saying in this case f of 1 equals 1? Alrighty, so 1 goes into the f function, and out comes 1. All right, kind of interesting. Now, what happens with this? This is f of 1, so this is our input. This is f of 1 right here, which is our output. That now goes into the f function one more time, so it goes into the f. There we go, that's looking beautiful. Well, what do you notice when I try to put 1 into the f function again? So the output, which is 1, becomes the input of 1, and I don't know, do you see that I'm getting the same thing again and again and again? So ultimately, that's it. Again, this happens to be what's called a recursion. If you kind of notice, could I keep doing this? F composed of F, composed of F, composed of F, et cetera, and then just have it as 1? And I would always get 1 as a final answer? Does everyone see that? Because every time I put 1 into the F function, I just get 1. So no matter how many times I do that, I'm just going to keep getting 1. Okay, kind of interesting there. Let's try this one, letter E. So again, I'm going to do this 2 different ways just so you can see it in action and you decide what's best for you. But if I'm just looking at this one independently, I have -2. -2 goes into the G function and I get an answer. After I get my answer, that number will go into the F function. So same deal. I'm going to start with -2. And it's up to you what you want to do with this. If you want to be visual, great. But you know, essentially, that -2 is going into the G function. So I'm going to do G of -2 exactly as it's stated up there. And not too much of an issue here, everybody. So 2 times -2. And then, let's see, add the 5. And so it looks like I'm just going to get 1 on that regard. Okay, so I've got that as 1. Perfect. Now, this is G of -2. Remember that. I'm going to just write it right here, G of -2. And that obviously is going to go into the F function. And notice what we end up getting. Same deal as before, just coincidentally, of course. When 1 goes into the F function, we've already gotten that. And it looks like I just get 1 as an answer. So -2 goes into G, I get 1. 1 goes into F, and I do get 1 as a final answer. All right. I do want to show you one thing just before we move on to the next piece. If you kind of look at this in a little bit, do you see that we did F composed of G of -2? Did anything kind of strike you as you kind of looked back on this a little bit? Look at letter A. Didn't we already create a function for F composed of all the G of X's? For any X value, that's what it should be. So when I say F composed of G of -2, can't -2 just replace the X's in our combination function right here? So long story short, didn't I already create a function composing F of G of X? And now that I have an X value, which happens to be -2, can I just use that? So here's what I'm going to do just off to the side, just to see that we get that same answer. So I've got F composed of G of -2, and I'm going to use this right here. So 4 times -2 squared plus 22 times -2, and what do you say we add the 29? I'm going to grab my graphing calculator for this and just see it unfold. I'm hoping that we get +1 on this, and we should certainly. Let's see if that does unfold. So, as I said, F composed of G of -2 would be 4 times -2 squared. Got that. Plus 22 times -2. And then add the 29. And let's see what we get. And there it is, of course. Alrighty. So a couple different ways to do this one. If you already have the function that you've created, you might as well just go ahead and put this input into the function. That's probably the easiest. But otherwise, you can do it exactly the way I did it the first time around. -2 goes into G, get an answer. That answer goes into F, and you get a final answer. Cool. Really, there's no limit to the number of combinations you can do and the number of times you can perform the compositions. Alrighty, let's go to the next piece. All right, let's make it a little more difficult in terms of the family of functions. The last problem, we combined a quadratic and a linear function together. Now let's do 2 rationals. Okay, so let's start out with letter A. So in this case, a very specific input, starting it out. So 1 is going to go into the G function, and then that answer is going to go into the F function. So let's see what this would look like from our perspective here. And so first and foremost, I probably want to do G of 1 So g of 1 equals 4 over x minus 1. And what do you notice in this particular case? Oops, sorry. Let me put the 1 in as I'm kind of thinking about it. There we go. And notice what you end up getting right away. Make me divide by 0, right? 4 divided by 0 can't happen. And so as a result, it seems like right off the bat there, f composed of g of 1 is undefined. Now there is a reason I put this in play, so keep it in the back of your mind if you would. But in the meantime, let's go ahead and do f composed of g of x. All right, so here's what I have. G of x will replace the inputs of the f function. So everybody circle g of x. There we go, looking good. And that replaces the inputs of the f function. So there are 2 inputs in that f function. And very simply, g of x is going to replace them. So what I get is 4 over x minus 1 plus the 3. And just to save ourselves a little time and energy, I'm going to try to be a little more visual with this. I'm just going to write that 3 as 3 over 1. I'm hoping that you're going to see that we're ending up with fractions within fractions here, so we're going to have to kind of deal with that situation. Okay, looking pretty good. What do you happen to notice here is when I've created f composed of g of x, I have a compound fraction, and so I do want to clean this up quite a bit here. So the way we've done this in the past is by looking at, in this case, the 4 fractions, 1, 2, 3, and 4, and coming up with the LCD. In this case, the LCD seems to be x minus 1, hoping everybody sees that. So I'm going to multiply x minus 1 into these 2. And if I do anything on the numerator of this overall fraction, this, then I also have to multiply it into the denominator. So I'm going to multiply into these 2 individual fractions by x minus 1. Okay, a couple ways we can do this maybe a little more visual. We've done this before last semester, so the expectation is we can kind of see this play out hopefully pretty quickly. Anyway, let's go ahead and see what we end up getting. So x minus 1 times 4 over x minus 1, hoping you do see the x minus 1s cancel, and I'll be left with just positive 4. Plus goes right here, of course. Now when I multiply x minus 1 into the 3 over 1, nothing cancels. So let's just do 3 times x minus 1. And if it's okay with you, I'm just going to write it as 3x minus 3. Okay, excellent. Repeat the process down in the denominator here, of course. So x minus 1 into this fraction right here. What happens to the x minus 1s? 1 on top, 1 on bottom. They cancel, and I'm left with that same 4 again. Here's my plus. Put it in play. And then one more time, let's reset and do it. X minus 1 times 2. Nothing canceled here, so I do have to do the 2 times the x minus 1. And I hope you see 2x minus 2. All right, again, just clean up the top a little bit, and I think we're good to go. So how does 3x plus 1 sound on top? And how about 2x plus 2 down on the bottom? And that seems to be a nice rational function. That looks really good. Okay. So we haven't introduced this term just yet with our combination function, but we're going to have to do it at this stage. It says determine the domain of the composition function. So here's what I created. Again, 2 functions combined together via compositions, and I created this function right here. This is our conclusion, essentially. Obviously, it is a rational function, and we do have to be careful in a rational function of dividing by 0. We already saw this in this example. So it looks like I would have an issue if x was -1. I'm hoping you see that right up there. So at this stage, and I'm going to kind of put it like this, at this stage it looks like x cannot be equal to -1. It can be any other number except for -1. But here's the thing. There's one piece missing. And maybe, just maybe, you're understanding why I did a particular part of the problem initially. Remember what I'm looking at. I'm looking at f composed of g of x and its domain. But in order to create this function right here, I really used g of x. This was integral to creating this right here. And do you notice when I tried initially to do f composed of g of 1, I was initially stymied, right? Couldn't do it because this never got through the first part. And so as a result, if I try to do f composed of g of 1, I have an issue. And the 1 also has to be excluded from the domain of our combination function right here. Okay? I'm hoping you kind of see that piece. Remember, this is f composed of g of x. But before I even created this, I tried f composed of g of 1 and did not have success. This 1 has to be excluded from the domain of the entire thing. So the 1 is excluded in addition to the negative 1 excluded that we saw after I created the function. So we'll obviously put a little conclusion in place here. There are a couple ways to kind of think about it. I'm going to write a couple different ways and basically pick whichever way works better for you. So here's, I guess, the most formal approach. So the domain of the composition function is the intersection of the domain of the created function. So we use the first two functions to create the third. And the domain of, and I'm going to put quotes around this, what I would call the inside function. In this case, of course, the inside function is g of x. I mean, I'll try to be visual with this as well. So let me play this a little out, and then I'll explain it one other way there, just trying to see what clicks. All right, so I have that, and just kind of looking at this piece, here's a number line, and I'm hoping you would all be like, you'd look at this. Sorry, give me 1 sec on that. There we go. You would look at this function and you'd say, okay, no worries at all. The domain can be any number but -1. And so that's what I would put right here. I'm going to just visually, an open dot on that -1. It can be any number but that -1, all right? The way we described it right here is that the domain of the inside function also affects the domain of the combination function. So if you look at this function, g of x, you see right away that x cannot be equal to 1. So as a result, that particular function, that would essentially be the domain. Everything but +1. Now when I talk about this buzzword right here, the intersection of the two, what I'm saying is it has to work for both of these values right here, both of these functions. So if you look at this, the values that work for both of the domains is everything but 1 and -1. Does everyone see that? Here 1 is excluded, here -1 is excluded, and so the values that have to work for both are everything but the 1 and -1. And so you can see this piece unfold. If you have more questions on that, please don't hesitate to ask. I'm trying to be pretty visual with something that's fairly complicated right here. The intersection of the two, meaning all the values that work for both of these, not just one, but both. The created function and the inside function. Okay, hope that works. If not, again, you'll let me know. All right, let's get into the last one here of the lesson. Just a nice quick application, putting it all together. Example 3. A meteorologist is inflating a spherical balloon with helium gas. If the radius is changing at a rate of 1.5 centimeters per second, express the volume as a function of time. Excellent. Now again, a couple different ways to do this. I'm just going to set the same bar that I have before. We want volume as a function of time. So time is the input. volume the output. If you look at the problem, it doesn't look like I have a direct connection between time and volume. So I'm going to have to create one, maybe using a secondary quantity. So I guess I'd look at this and, I start out with t. That's my input. And the question is, what do I know if I have the number of seconds? Well, if you look at part A in a little detail, it does say that the radius is changing at a rate of 1.5 centimeters every second. So if I have the number of seconds, I can probably just multiply that by 1.5, and that would give me the number of centimeters for this radius. So it seems to me, trying to make somewhat of a long story short, that if I have time, then I can easily calculate the radius. The radius is 1.5 times the number of seconds, 1.5t. Okay, so inputs, output. Now here's where the idea of a composition comes into play, because that radius actually happens to be the input of a secondary function. As we know from geometry, if I know the radius of a sphere, then I can figure out what the volume of a sphere is. Now volume happens to be of the sphere, 4/3 pi r cubed. And so as a result, I can kind of use that idea. I'm going to go ahead and, I don't know if this is the best idea here, but I'm going to put it here nonetheless. Yeah, let's do that. Okay, so if it's 4/3 pi r cubed, that's great, because I know what the radius is in terms of time. So as a result, I'm hoping you kind of see this play out as 4/3 times pi. Now instead of the radius cubed, I've got 1.5t cubed. How neat. And notice in this particular case, I have volume not as a function of the radius, but I have volume as a function of time. So let's see where we can kind of put this into play. I'm thinking maybe over here would do. So volume as a function of time. 4/3 times pi times 1.5t, and that's going to be cubed. I'm going to just simplify this for you. I mean, that is perfectly legitimate. I just have it on my paper here. If I kind of cube 1.5, that would be 3/2 cubed, so that's 27/8, and then kind of work with the 4/3 here. I have it on my paper, so, and I'm looking at the clock and just want to get this taken care of for you. I end up simplifying that to 4.5 and then t cubed. So if I remove the parentheses and clean this up a little bit, as a decimal, this would be 4.5 pi. Okay. Again, I'm going to leave that. Try that math if you don't mind simplifying it as well. Perfect. Well, if you look at letter B, now that we have volume as a function of time, any input should be able to create the output without too much issue. So guys, let's see if we can do this in 2 quick steps here. So V of 4 essentially, and V of 5. All right, let's go ahead and get both. So bring the calculator on up, and here's what I have, 4.5, and what do we say, pi, got that, times 4 cubed, and looks like I have about 905, give or take, cubic centimeters. And I'll do the same thing just quickly with the 5 seconds as well, just so we can kind of bring this to a conclusion for you. And 1,767 cubic centimeters. All right, perfect. So let's get those in play. 904.78 roughly cubic centimeters, 1,767.15 cubic centimeters. If you notice, and we've had this discussion before when we've worked with functions, is essentially this composition is nothing more than substitution. This replaces the r of that function right there. Okay guys, I'll wrap it on up at this stage. If you have any questions at all, please don't hesitate to ask. Thanks.